All right, so with exponential families, most of the ones that you're going to see on this is very, very straightforward. It's stuff that you've seen before. All right, so first thing I want you to do is in Desmos, take a minute, graph this function right here. So f of x is equal to 5x or y is equal to 5x, 5 raised to the x power. And then do a quick sketch of the graph. And that's all I want you to do. All right, don't start answering the questions yet. So again, exponential family worksheet. For number 1, put y equals f of 5x in your in Desmos and draw a sketch of the graph. Do not answer any of the questions yet. And your sketch doesn't have to be exact. Just try and get it fairly close. All right. So let's look at this together. So if you graph that in Desmos, you should get a sketch that looks something like this. All right. Now, let's just answer some questions. Where does the graph cross the y-axis? So in other words, your y-intercept. What's my y-intercept? You can either look at your sketch or you can look at Desmos. It crosses at 1. So the y-intercept is at the point 0, 1. Now, it then asks us what values of x does the function use. So in other words, it's asking us for our domain. So what is the domain of this function? So for this, I would probably look at Desmos. So if I'm looking at Desmos, what x values does it look like I'm using in my functions? What's kind of like my interval here? So remember, domain, you're going from left to right. So what's my lowest x value? So my leftmost x value. What do you think? It's negative infinity. Why? Why do you think that? It never ends. It keeps going on forever to the left. What about my highest x value? What do you think? Positive infinity. It keeps going on forever till the right. So my domain is from negative infinity to positive infinity. Now, it then asks us for the y values, so our range. So remember, bottom to top. So if we're looking at our graph again, where does it look like our y values stop? Or what looks like our bottommost y value? So ignore the x-axis, just look at the y. In fact, there, now we're just looking at the y. So what y values does it look like our graph stops at? Where? 0. So our bottommost y value in this case is 0. What do you think our highest y value is? So look at the graph again. I would say positive infinity, yes. So guys, a little trick of the trade. When you're doing domain and range, if the other axis is throwing you off, hit the little wrench key in the top right-hand corner. And right next to where it says x-axis and y-axis, you can check and uncheck them. So like if you're doing domain, you just want the x-axis, uncheck the y-axis. When you're doing range and you just need the y-axis, uncheck the x-axis. So it may just be a little bit easier for you to see and a little less confusing. All right. So that's just kind of a strategy that you can do for domain range because I know it's a pain in the butt. Now, here's my question to you. Do you think the graph will touch or even cross the x-axis? So take a minute, look at Desmos, think about it. All right. Thumbs up if you think it will touch the x-axis. Thumbs down if you think it won't. 1, 2, 3, go. Okay, I got some mixed reviews here. So, for those of you who said it will, someone tell me why you think that is. And again, there's no right answer. Just what's your opinion? Why do you think it's going to touch? So, someone who had their thumb up. Come on, guys. Someone give me something. So, if you have your thumb up earlier, why did you think it was going to touch the x-axis? Just why did you think it? Like, your opinion. Why did you think it? So, you're telling me that you just threw your thumb up just randomly? All right. For those of you who have your thumb down, can someone tell me why you put it down? Unless you're just guessing. Corey. Right. It kind of looks like it's going along the x-axis, but it doesn't actually go over it. So in reality, the graph does not. The graph does not touch or cross the x-axis. And the reason for that is something that we're later going to learn as a horizontal asymptote. And I'll explain what that is in a little bit. But just for argument's sake, if you look at Desmos, all right, and you go like really, really far into the x's, and then you zoom in, because it looks like it's just straight on the x-axis right now. But if you zoom in like a whole lot, like really, really tiny, and I gotta go, Lord. Sometimes if you go too far, it won't let you do it. So if I zoom in really, really tiny, right there. So I have zoomed in super duper tiny. The x-axis is this black line here. The function graph is right here in that red line. It gets super duper close to that x-axis, but it never actually touches it. It gets infinitesimally close. And I had to zoom in to the point where I'm in like a lot of decimal places. All right. Like you can't even see it to the naked eye unless you zoom it in that much. But it will never cross that x-axis right there. All right. Actually, it does that all the way across. Because what happens is that the decimals start getting so small Desmos starts saying that it's at 0 because they're so infinitesimally small. But in reality, they don't actually cross. That's what Desmos does. All right. Now, that means that we have a horizontal asymptote, which is basically an asymptote is just a straight line that you're, whether it's horizontal or vertical, that we're basically saying, yeah, you're not crossing here. All right. You cannot go over me. It's like the borderline. It'll get infinitesimally close to that line, but it will never cross. So the graph will never cross this line. Now, if we were to write an equation for it, Gavin, just put the test on my desk. Now, if we were going to write an equation for it, what do you think my equation for that line would be? So this horizontal line, what do you think the equation of that line would be? So what do you think? So it's just a horizontal line. So think way back to Math 1 when you were writing equations for horizontal and vertical lines. It's right. It's y equals 0. So my equation for the horizontal asymptote is y equals 0. That's how I would state it. Now, that being said, I now want you guys to take a minute and graph all 3 of these functions in Desmos and state their y-intercept, their domain, their range, and their horizontal asymptote, and do a quick sketch on the graph. So basically just fill in that chart. It's take about 5-6 minutes, fill in that chart. Mm-hmm.
My mom said that she called the office, but that I'm doing check that.
Okay, so just check Canvas for notes and stuff like that. Mm-hmm. The asymptote is the thing we just talked about up top. So the horizontal line that doesn't cross. So where does it look like the graph doesn't go over? So that line right there, where do you think it's, so this line right here, or right here. All right, this is our asymptote because our graph looks like it gets super duper close to it but never crosses that line. So it almost looks like your graph would be like right on top of it. No, the asymptote in this case, because it's on the x-axis, is y equals 0. Because your y value is 0. It doesn't cross the y. So typically it's whatever your range value is. Your lowest in your range, yeah. Mm-hmm. So again, guys, you're just filling in that table and sketching those 3 graphs on that graph. Yes. Remember, domain is or range. Range means from your lowest y value to your highest y value. So get rid of the x-axis. Y values. So it's what shelter kind of. What do you think? So your lowest is -7. There's the highest. Because it's right going from. So keep on. All right, I'll give you guys another minute. It's okay if you don't finish. So we're gonna talk about it. Honestly, if you don't sketch the graph, that's okay. Just at least get that table filled in. All right, so for time's sake, I gotta move on, but check your work. So again, if you don't sketch the graphs, that's okay, but I at the very least want that table. Now, what do you guys notice about that table with the inputs in that table? What does it look like? They're all the exact same across the board. However, so some pattern that we see is all 3 functions have the same key features listed. So all the listed key features, so y-intercept, domain, range, and asymptote, they're exactly the same across the board. However, if we look at the graphs, there still are some distinct differences. So the purplish looking graph is the 2 to the x power, the green is the 3 to the x power, and the blue is the 1/2 to the x power. What do you notice? What differences do you notice between the green and the purple? So 2 to the x power and 3 to the x power. What do you notice? So there's no right answer here. I just want to know what you notice about those 2 graphs. So these 2 graphs right here, these 2 lines. What do you notice? They're what? These 2.
They're wider than or the red one's wider than the green one.
Right. This one looks like it's a little bit wider than this green one. In other words, this green one looks like it's steeper or it's going up faster. What about the blue one in comparison? It's going the opposite way. So instead of looking like it's going up, it looks like it's going down. Now there's a reason for this. Can anyone guess why? Look at the original functions. So these 2 are these 2 lines here, and this one is this line here. What do you notice? It's less than 1. So in other words, these 2 have what we call base values greater than 1, which is why they look like they're increasing. And this one has a base value less than 1, or a fraction essentially. So that's why it's decreasing. That's an actual rule. So the form that you're used to from Math 1 is that you're used to the form y equals a times b to the x power. I'll tell you what a means in a little bit, but b in this case, because these are all b values, is your base. All right. Now, if your b value is greater than 1, your graph will increase. But if your b value is between 0 and 1, your graph will decrease. So in other words, if it's between 0 and 1, that means it's a fraction. So basically, your b value is whatever the exponent of the x is connected to. Now, number 3 is going to show us what that a value means. All right. So take a minute, look on the back side, and then do the exact same. Fill in the table for number 3. So I don't really care about the graph sketches. I just want the table filled in. Yes.
The last part of that sentence. So, after like saying the same what the features listed.
One's increasing the other. All 3 functions have the same key features. Yeah. Yeah, it's really light, but it says key. It's easier to read on my computer, but then when you look at that, it's like, ugh. So take a minute, fill in the table for number 3. And one of the columns you don't have to do again because they already did it for you in the previous one. So one of those columns you should already have answers for. Again, I just want that table filled out. Don't worry about the graph sketches. I'll give you guys one more minute. All right. Check your answers. Again, don't worry about the sketches. I just did it so it's a little easier to see. But looking at that table, what's the only part, the only key feature that was different between those three functions? The y-intercept. So if we look at the y-intercept specifically, all three of the y-intercepts are different. However, the domain's the same, the range is the same, and the asymptotes are the same. What is going on with our equations up at top to make those y-intercepts different? What do you think? What consistencies do you notice?
It's the number outside the parentheses.
It's the number outside the parentheses. Because if we think about it, for this 2, what number would technically be outside the parentheses of that 2? 1, because 1 times anything is itself. So when we were talking about y equals a to the bx, we said that b was its base, and a, in this case, actually represents its y-intercept. So the y-intercepts are different because the a value, or the number outside the parentheses, is different. Now, all of that a value changes is the y-intercept. And then it may also change the scale with like how wide or how narrow it gets. So just like with transformations. So think about transformations. So back to unit 1. All right. Looking at the graphs, they don't shift up, they don't shift down, they don't reflect over anything. So clearly we're dealing with a dilation. If this one is the original, so think back to your transformations. What kind of dilation happened to the middle column, to the middle function? So they're multiplying a 3 to the outside. So again, this is compressions and stretches. That's what dilations are, compressions and stretches of the vertical and horizontal variety. What do you think? So first off, will the red graph get wider or narrower than the green graph? What did it do? Did it get wider or did it get narrower? Narrower. Because it looks like it's getting steeper faster. All right. So if it's narrower, that means that it's a vertical what? So this is a vertical dilation, but is it a stretch or a compression? If it's getting narrower, it's a stretch. So think about the rubber band example I did way back in the day. All right. If you stretch it, your rubber band gets thinner. If you compress it vertically, your rubber band gets wider. So this is actually a vertical stretch. Where on the opposite side, the blue graph gets wider. Tomas? Yeah, he's right here.
Are you coming to donate blood?
Yeah.
Okay.
Oh, sorry, Tomas. I didn't check time. So on the other hand, this graph is actually a vertical compression of the original. It got wider. So that's just something good to note. But essentially, the main takeaway is that that a value changed our y-intercept. All right, last table. So take a minute, fill in that last table. Oh, here, I'll give you guys back the... There you go. So fill in that last table. All right, guys, I'll give you another minute on this table.
That's your X-ray. No, range is your lowest Y value. So, like I said, we wanted to, we could get rid of your X-axis. And just look at the X.
All right, guys, check your answers. All right. What did you guys notice? So the first two equations specifically, what kind of happened? So we did a lot of graphing 2 raised to the x power. How did those two graphs, the blue and the red, differ from the ones that we did with just 2x previously? How do they differ? What changed? So specifically, from the ones that we did up here and the ones we did on the previous page, what's the major thing that changed? Landon. The range and the asymptotes changed for these two. So if we look right here, our ranges and our asymptotes changed. So instead of being y equals 0 and the range being from 0 to infinity, they changed. Why do you think that is? What's different about it? Why do you think that? Why do you think the range changed? Why do you think the asymptote changed? What happened? So look at the function specifically. What's different than what we already had, Haley? Kind of on the right track. It does have to do with the adding and subtracting, though. Let me ask you this. Did the ones that we did previously, so the ones that we did in the table before that, were we adding or subtracting something outside of the base? No. We did not. That's what changed. We were adding and subtracting things to the outside of our base. Now, think back to your transformations. What type of transformation would that be? So think about it. If your asymptote started at 0, and then for the blue graph, we added a +1 to it. So now the asymptote went to y equals 1. What happened to the graph? Think transformation. So shift, dilation, reflection. What happened? We did a whole lesson on this in the last unit. Come on. So we're adding something outside of the brackets. It's going up and down, or it's a vertical shift. So here we shifted up. Here we shifted down. All right? It was a vertical shift. That's why the asymptotes changed, because vertically speaking, your asymptotes will move with the graph. So if your asymptote starts at 0 and your graph, and your entire exponential graph shifts up 1, the asymptote goes with it up 1. If you start at 0, because 0 is kind of like the parent function, it's where it starts. If your asymptote's at 0 and you subtract 3 on the outside, and if your entire graph goes down 3, your asymptote goes with it down 3. All right? So that's why the range of the asymptote was different. What about the last one? So the asymptote didn't change, the range didn't change. What did happen though? The y-intercept changed. So we're used to a 2x graph. So 2 raised to the x power, we're used to that being just 0, 1. Why is our y-intercept now 0, 1 half? So what I'm saying is typically when we have y equals 2 raised to the x power, our y-intercept is 0, 1. Well, this is still a 2 raised to the x power kind of graph. What's the only difference? The -1 up here. So this -1 right here, the -1. What technically happened to that 2x graph? So if I'm looking at Desmos, all right, I already have it graphed. This would be your parent graph. What happened? So this is our starting point. All right. What happened to the graph? It's pretty much the exact same graph, but something happened to it. Landon. Didn't get wider. It's the exact same graph. Exact same steepness, exact same graph. But something did. It didn't shift up, but you're right on the shift part. Didn't shift down either. It shifted right. So the new point, if we look at 0, 1, the new point would be right here at 1, 1. All right, that's where it shifted. Whereas right here, this y-intercept is 0.5. Its original spot was at -1, 0.5 on the blue graph. All right. So what happened was it shifted to the right 1. Why is that? So I'll give you a hint. The exponents considered your brackets. The -1 is inside the brackets. It's being subtracted to our x value inside the brackets. So we actually shifted right. Nothing else changed about that graph except the y-intercepts is slightly off because the graph shifted left and right. So vertical shifts can change your graph, can change your asymptote. So vertical shifts can change your range and asymptote. All right. Very important to note that. So the final form of an exponential equation, so the one that I showed you was a very basic form, but we added on the 2 parts. We added on the h and we added on the k. All right. I already told you that the a value is your y-intercept. Your b value controls its base as well as how fast it goes up, so its steepness. What does your h value control? What did we just say it controlled? How it goes left and right. So your h value just controls whether it goes left or right. Now, your k value controls whether it goes up or down, but it also controls what? What changed in that table with the K value when we added or subtracted a K value to it? The asymptote and the range changed. So it also controls what your asymptote is. And it also controls what your range is, or where your range starts dash ends, depending on what type of graph you're looking at. So, very important things to note there. So again, the reason we were doing that is because we wanted to see what was going on with our graph. All right. So that was just kind of to get you guys to start seeing those key features and how they affect exponential graphs. So now let's look at that journal entry. All right. So with this journal entry, we're going to do half of it today and then the other half later on in the unit, and you'll see why in a second. So take out that foldable, which is that journal entry that I had you guys grab. So this one. And I'm looking, and it looks a little different on my page than yours, but I'm going to look at the side that says exponential functions. Say one more time. Not really. Not for right now, anyway. All right, so we're on the foldable. I'm only going to look at the exponential side. We'll do the logarithmic side later. So, with exponential functions, all right, its base form, like I said, is f of x equals a times b of the x. All right, where a is your y-intercept and b is your base. It can also be referred to as your common ratio. Essentially, what that means is if you looked at a table of the points on an exponential graph, the y values would be multiplying between each other by whatever your base value is. So if your base value was 2, if you went from a y value of 1 to a y value of 2, you multiplied by 2 to get there. Now, there are two types of exponential graphs. There's increasing and decreasing. This is an increasing exponential graph. And like I said, that comes from when that b value is greater than 1. Now, in its base form, so in this form, well, I'll come back to that in a second. Now, decreasing graph is this next one. So this is the decreasing graph. And remember, like I said, that means when the b value is between 0 and 1. So in other words, it's a fraction. B is a fraction. And by fraction, I don't mean like 7 over 4. I mean like a true fraction. It's truly smaller. The numerator is truly smaller than the denominator. Like it's a true piece of the pie. True fraction. Yes, it's a true fraction. So like 2/6, 3/5, things like that. The numerator is smaller than the denominator. Now, yes, yeah. Exponential graphs always have a horizontal asymptote. All right. And remember, the way you write a horizontal asymptote is that it's a horizontal line and it'll be y equal to whatever y value that line falls on. So y, the horizontal asymptote, you always write it as y is equal to some number. If I ever asked you to tell me what the horizontal asymptote is, you have to say y equals this number. If you just give me the number, it's wrong. And the reason I say that is because when we get to vertical asymptotes with logarithmic, it's completely different. All right. So for our decreasing graph, our horizontal asymptote will be right here at y equals 0 because it's just on the x-axis. And for our increasing graph, our asymptote is here, also at y equals 0. Now, something to note is that this base form, because there's nothing being added or subtracted on the outside, if you see a function a times b to the x power, and there's no plus or minus on the outside of b, so there's no number being added or subtracted to our base value, then the horizontal asymptote is always going to be y equals 0. So remember, the asymptote only changes if you're adding or subtracting a number outside or on the other side of that b value. So if there's no plus minus here, or just plus or minus, that's what I mean by that. There's no plus minus, your horizontal asymptote is automatically at y equals 0. Now, let's look at some examples. So again, I'm just looking on the exponential side. We'll do the logarithmic side later. So for time's sake, I'm just going to fill in the tables for you. So essentially, this is actually no. This is where your power chart comes in handy, because this is the exponent. Your x values with exponentials are always whatever your exponent is. So essentially, we're saying this is 2 to the negative 3 power, 2 to the negative 2 power. That's how we find y. So look at that green power chart that I had you guys fill in at first. All right. What does it say 2 to the negative 3 power is? Oh, well. What does it say 2 to the negative 2 power is? 1/4. What does it say 2 to the negative 1 is? 1/2. 2 to the 0. 2 to the first. 2 to the 2 squared. 2 cubed. Good. Now, take a look at those negative exponents, so the negative x values. How do they compare to their positive counterparts? What happened? So the negative 2 and the negative 1. Negative 2, we had a y value of 1/4. Negative 1, we had a y value of 1/2. But on the positive side, 1 is 2, 2 is 4. What happened? Why do you think that is? You guys remember exponent rules? So, in other words, what happens, and I believe that's also on your power sheet if you filled it in from the notes, what happens if you raise any base to a negative power? What happens to that negative exponent? It gets moved to where? So guys, for review's sake, if you have a negative exponent, it gets moved to the opposite side of the fraction bar. So if the base is in the numerator, it gets moved to the denominator. So this is 2 to the negative 2 is the exact same as 1/2 squared, which 2 squared is what? 4, hence the 1/4. So what do you think 2 to the negative 3 power is? 1/8. Good. So make a note of that, because you do need to know how negative exponents work. Now, I'm going to do a very quick sketch graphing these points. So I got 3 at 1/8, 2 at 1/4, negative 1 1/2, 0 1, 1 2, 2 4, 0.38. So my graph will look something like this. All right. What's my domain of that graph? All real numbers or from negative infinity to positive infinity. What's the range? Guys, we did this one like 20 times on that worksheet. What's the range? 0 to infinity. Because its horizontal asymptote is where? At 0, or the x-axis. So here's the horizontal asymptote at y equals 0. Now on the flip side, so guys, the great thing about 1/2 of x, all right? Let's think about this for a second. If I'm doing, let's say 1/2 raised to the negative 2, all right? By power rule states that I multiply to this exponent of 1 and this exponent of 1. So this equals 1 to the negative 2 over 2 to the negative 2. By power rule, these two swap places. So this is 2 squared over 1 squared. So 4 over 1. So 1/2 raised to the x to the negative 2 power is actually what? 4. So what do you think 1/2 raised to the negative 3 is? Based off of that assumption. 8. What about 1/2 to the negative 1 power? 2. What about 1/2 to the 0 power? Still 1. Anything raised to the 0 power is always 1. What about 1/2 to the first power? Just 1/2. 1/2 to the second power? 1/4. Because if you think about it, again, if you had 1/2 squared, you'd have to do the power rule. This will be 1 squared over 2 squared. So that'll be 1 over 4. So what do you think 1/2 cubed is? 1/8. So in other words, the y values between the first graph and this one switched. All right. Because this graph is going to look like it's descending. So I'm going to do a quick sketch real quick, given my points. And again, it doesn't have to be perfect. Now, this graph still has a horizontal asymptote of y equals 0. The domain and range are still exactly the same. It's still negative infinity to positive infinity and 0 to infinity. The only difference is that this graph decreases because it has that b value between 0 and 1. It's a fraction. And this one increases because it has that b value greater than 0. Not greater than 0, greater than 1. So, essentially the exact same base, except one is in fraction form, the other one is in whole number form. So you need to know the difference of those basics. Now, we're going to stop there for that foldable. We'll fill in the other half later when we get to the logarithmic side of things. Logarithmic?
Yeah.
You'll find out.
It's a big one. My friend said that she doesn't like doing math like that. I'm a little afraid.
Yes. Yes. All right, the very last thing that we're going to do together as a class is you do have a kind of very short delta assignment. that introduces exponential functions. So basically what we've been talking about today. But there's a couple of problems that I want us to go over together as a class. All right. Why did I do that? So I want you guys to log on to Delta Math and select the one that says Math 3 Unit 2 Intro. And just open it up. Don't click on any numbers yet. Just open it up. We're going to do a couple of these problems together. There's some single problems that will be the exact same that you guys had. So, the first one we're going to do is the one that says match the exponential equation in context single. All right, so it's the third one down. So take a minute, get to Delta Math, look at here. My screen looks different than yours. This is my teacher mode. So get logged on to Delta Math, hit Math 3, Unit 2 Intro. Yes. Can I not? Well, now it should be. So refresh it, it should pop. All right. Now you guys might want to jot this down on a scrap sheet of paper because these will basically show you how to work out the rest on your own. All right, so I want you guys to hit the first single problem, which says match exponential equation and context single. It's 3 from the top. So 3 sections from the top. So when you click on it, you should see exactly this problem. So if you don't see exactly this problem, you're on the wrong section. It's in Delta. All right. So again, this is review from Math 1. So again, you might want to jot this down either in your journal, like off on the left side of that foldable, or you may want to jot down on a scratch sheet of paper. So Ella has a collection of vintage action figures worth $430. She appreciates a rate at 4%. Which equation represents the value of the collection after 7 years? So we're simply just writing the exponential equation. So before I even tell you, let's just do a guesstimate type thing. Which answer choice do you think this will be? So hold up 1 finger for the first one, 2 fingers for the second, 3 for the third, 4 for the fourth. Take a minute, look at it. Just make a guess. All right, just an estimate. All right, ready, set, go. What do you think? I see some 2s, I see some 3s, I see some 4s, some 4s. Okay? So, the answer to this one is 2. Let me show you why. This is what we call an exponential growth or decay problem. So you learned this way back in Math 1. The general formulas for exponential growth and decay. The growth formula is typically y is equal to a times 1 plus r raised to the t power. The decay formula is typically y equals a times 1 minus r raised to the t power. Where a for both of these are your starting value or initial value. R is your rate of increase or decrease. That's usually given to you as a percentage. and t is how much time passed. And it's the same for both. Those values mean the exact same thing for both. Now, why is this a growth and not a decay? What does growth imply? It's appreciating. So growth implies that it's growing or that your graph is increasing. Decay means it's decreasing. So since it says appreciates, that means that it's a growth. Now, what do you think my rate is here, or my R value? The 4%. So this 4% right here is my rate or my R value. Now, when we're putting that in the formula, we got to convert that percent to a decimal. How do I convert that percent to a decimal? Well, what's the highest percent you can have? 100. So if I have 4 of 100,
Two decimal places.
yeah, you can either do the 2 decimal places to the right method, or you can just do 4 divided by 100. And you can put that in your calculator. It should give you 0.04.
Two decimal places to the left, right?
To the right. So if we had 4 here, the decimal's here, you go, oh yeah, it is to the left. I'm thinking backwards, guys. Do as I say, not as I do. So, now we have all of our values except our A value. Where did it say I started? 430. So this right here is my starting value or my A value. Now I got everything I need to put it into this formula. So I have y is equal to 430 times 1 plus 0.04, which is my R value, raised to the t. Now, what's my t value in this case? Because they did give it to me. So t represents time. So what's my only value that has a unit of time after it?
7 years.
7 years. That's my t. So it'll be raised to the 7th power. And then all they did was simplify that. So this would be y is equal to 430, 1.04 raised to the 7th. And that's how they got this. So the biggest takeaway are these 2 formulas right here. You will see them again. All right, that's the biggest takeaway here. Yes. Yeah. All right. We'll pick this up tomorrow, first thing tomorrow. So your exit ticket for today is, let's just do another one of these. All right. Do that problem as your exit ticket. So I want you to state what the correct function is. Can I erase this? I'll leave the formulas on the board. I'm going to erase this. Well, I tried. So do that one as your exit ticket. Mm-hmm. Yeah, sure.
I don't even know the space in my thing, so no.
By the way, this is not the answer. It's just a board. Or it could be the answer. I don't know.
Maybe it's not, she's just tricking everybody.